Let us study the band structure in semiconductors. For this we can write that band structure in semiconductors are similar to insulators, which we have just now studied in the previous article, that in insulators conduction band exists high above the Fermi level in valence band. But here we can say band structure in semiconductor are similar to insulators, but these have forbidden energy gap very small, as a conduction band is close to Fermi level and valence band. Like in insulator, the separation between conduction band and Fermi level is more than 5 electron volt, but in case of semiconductor it is quite less. And we can also write if Fermi energy gap is less than 2 electron volt, then we can say at room temperature electrons gain this energy by thermal agitation only, and transfer to conduction band. And that implies that in semiconductors, as Fermi energy gap is less than 2 electron volt, at room temperature electrons will exist in conduction band, and semiconductor can conduct electricity at room temperature. But when we talk about semiconductors very low temperature, then at very low temperature no electrons will be there in conduction band, and semiconductors will behave as insulator only. You can also write at very low temperature semiconductors behave as insulators. Let's discuss about the band structure in semiconductors. That will make the phenomena more clear to you. If we just have a look on this band structure diagram, we can see at very low temperature in semiconductor conduction band there are no free electrons, as free electrons are filled only up to valence band, and this is the Fermi energy level up to which electrons are filled. Lower orbitals are obviously, or lower orbital bands are also filled completely. But when we talk at normal temperature, the electrons are able to attain some energy, because of which some electrons of conduction band will shift to the conduction band. So in this situation we can say this is the Fermi energy gap delta Eg, which is having a value less than 2 electron volt. This much amount of energy electrons will gain due to the thermal agitation by room temperature. So these electrons will shift to conduction band. So in this situation, when from valence band electrons will shift to conduction band, some electron deficient spaces are left, which we are denoting here by small circles. These electron deficient spaces are termed as holes in valence band, which are considered to be equivalent to plus E charge, because valence band was earlier neutral, and if electrons are shifted to conduction band, these are electrons which are transferred to conduction band. Some electron deficient spaces are developed in valence band because of transfer of electrons. So these are equivalent to positive electronic charge, which are termed as holes, which are developed in valence band. Now in this situation, as this substance at room temperature is having free electrons in conduction band, these can conduct electricity. Even in later sections of this topic, we'll study that holes also participate in conduction of electricity. So at room temperature or normal temperature, semiconductors behave as conductor. But if temperature is further increased, more electrons will shift from valence band to conduction band, and because of which conductivity increases. This is the reason why on increasing temperature in case of semiconductors, conductivity increases and its resistance decreases, or we say its temperature coefficient of resistance is negative. Whereas in metals, we know well that on increasing temperature, rate of collision substantially increases and resistance increases and its conductivity decreases. That's why in metals, temperature coefficient of resistance is positive. As we already discussed on the previous sheet that in a semiconductor, there are two possibilities of conduction of electricity. The first one is by electrons in conduction band, and the second one is by holes, which we already discussed. These are electron deficient zones in valence band. So, once a potential difference applied across a semiconductor, current flows due to two kind of charge carriers. One is by electrons in conduction band, other is by holes in valence band. Let's discuss once again about the same phenomena with the band diagram in detail. In this band structure, we can see that at room temperature, some electrons in a semiconductor valence band transfers to conduction band, and these can conduct electricity because now these are free electrons. Now say if a potential difference, high potential and low potential is applied the semiconductor substrate, then electrons in conduction band will shift toward high potential, and these holes which are equivalent to plus E charge will shift toward low potential end. Another important point regarding how holes will transfer is basically a phenomena of hole conduction mechanism. We'll discuss in coming sections of this topic. But precisely you just keep one thing in mind, that holes can transfer toward right if more electrons from one hole to another start moving toward left, then it appears that holes are moving toward right. So, if positive charges in a substance are moving toward right, these will produce current in rightward direction, and if electrons in conduction band are moving toward left, this will also constitute a current toward right direction. So, we can say total current in a semiconductor is constituted by both the currents because both currents are in same direction. And as the temperature increases, we can say more electron hole pairs are generated, because of which more current will be there in the substance, and we can say its conductivity increases. So we can simply write which we already discussed, that with increase in temperature, conductivity of a semiconductor increases, hence its alpha is negative, which we already discussed.